Okay, this question here is an orbital mechanics question, coupled with some straightforward, well, not necessarily straightforward, but straightforward-ish geometry. A whole load of information that we'll have to refer back to as we're doing other questions. And first, 2 essential features of an orbit needed for a satellite to appear geostationary. 1, it needs to be a orbital period of 24 hours. Now I know that it's actually a little bit less than 24 hours. It should be 1 sidereal day, but that's what they put as the answers. The other thing it needs to have is it needs to have either an equatorial orbit, or more accurately, it needs an inclination of 0 degrees. Okay, so line 7 of the passage to complete 1 orbit. So I will need my orbital mechanics. Formulas. Okay, so the satellite mentioned in line 7, how long it takes to complete. So we're actually given that it has a radial velocity of 2.5 times 10 to the minus 4 rads per second, which actually means that the time taken should be 2 pi divided by 2.5 times 10 to the minus 4. I want it in seconds. We end up with 2.5 times 10 to the 4 seconds, or 2.51 times 10 to the 4 seconds. Okay, to show that at a distance of 1,200 kilometers from the satellite, the beam has a width of 1,900 kilometers. So we need to figure out theta here. Theta is wavelength divided by diameter of the dish, according to this formula. We got 1,100 megahertz using a 1.7 meter dish. So, first things first, C is lambda F, so lambda equals 3.0 times 10 to the 8 divided by 1,100 times 10 to the 6. So we end up with 2.7 times 10 to the minus 1 meters for our wavelength. Theta is equal to lambda over d, which is 2.7 times 10 to the minus 1, divided by 1.7. .6 times 10 to the minus 1 radians. And our arc length here, which will be our width, is equal to theta times orbital distance. Use a capital D for that. Well, it's actually technically altitude, not orbital distance. Okay, 1,925 kilometers, which is approximately 1,900 kilometers. Show that the receiver can remain in contact with the satellites for no more than about 20 minutes each orbit. Okay, so for this one, what we're going to do is we're going to look at how many radians it is that gets swept out by 1,900 kilometers. If we have a radius of 6,400 kilometers. And that's just 1,900 over 6,400 is you could also do 1925 if you want to, but 0.30 radians. Okay. So time is theta divided by omega. Oh, divided by 2.5 minus 4 is just shy of 1,200 seconds, which divided by 60, 19.8 minutes, which approximately equals 20 minutes. Oops. Okay, so this last one here, we have the exact same satellite and it's moved into a higher orbit. Discuss with reasons how this affects the signal strength and contact time for the receiver at the South Pole. Well, first things first, the signal strength will decrease as the transmitter is farther away. The other thing is the intensity will drop. because you'll be sweeping out a larger area. Okay. The signal strength would be proportional to the distance squared, and the area covered, that should actually also go with proportional to distance squared. The next thing, though, is it will be in contact longer. As the orbital speed or period must be longer at a higher altitude or at a higher orbit. And that should be enough.